So today we're going to find lengths of curves. So if I have a random curve, and I want to find length. Well, right now we don't know how to find length of something that is curved unless it's a circle. How do I find the length of the outside of a circle? Circumference, 2 pi r. But I could approximate. How do we usually approximate things that we don't know? Usually we take something we do know. What do we know how to find the length of besides circles? A line. I know how to find the length of a line. So if I took from here to here, did a straight line, give me something close. You know, from here to here, straight line, that one would even be closer. But then if I did from like here to here, not very close. But still, we could approximate the length of our curve by adding up a whole bunch of lengths of lines. So, how do we find the length of a straight line? What formula do we already know? We have to think back. All the time when you were in Algebra 1.
Distance.
Distance is?
What is it? Oh. Square root of... I can't remember if it's y or x first. Oh, it's x. What's the second one minus the first one? Squared plus y. Yeah. You know.
You know, I was thinking, you knew. Plus
That.
y2 minus y1 squared, which is really just Pythagorean theorem. It's a form of the Pythagorean theorem. If we, just a random side note, if we have 2 points, the way they found this was they connected them to make a triangle. If this point is x1, y1, this is x2, y2. Find the distance, x2 minus x1. Find the distance, y2 minus y1. We're just finding the hypotenuse of the triangle. So this random connection that maybe you never made before. They may have, but when you first see it, usually making those deeper connections isn't as easy as when you're like, oh, I know how to do this, and you're not worrying about how to actually do the distance formula anymore. You're like, oh, my mind is freed up to do other things. A random side note. My husband's family swears he did so much better after one day, and this was like when he was in like junior high. It's like, oh, Barney Rubble, Fred Flintstone, they all have to do with rocks. And they say he got smarter because it freed up his brain to work on other problems. Just because he had been subconsciously working on that, you know, for years. That's a funny story. Okay, so what's another way to write x2 minus x1 in a more calculus-y fashion? What do we write for change?
X.
Delta x. Delta y. But our ultimate goal every time when we're adding up stuff is to get that stuff to be infinitely small, right? We want delta x to disappear. We want it to go infinitely small. But another problem is when we're integrating, if I just slapped an integral on this right now, what would be our problem?
You have multiple variables.
Multiple variables. That is an issue for us. So they did something tricky. They said, well, we know when we integrate, we want dx, which if we're in our non-limited, so we go from delta x to dx if we take the limit. So before we've taken the limit, we still have delta x, right? We need that to tell us to integrate with respect to x. But I'm going to be a little tricky. I'm going to say instead of just delta x, I'm going to say this is the square root of delta x squared. So it's something that could go inside the integral. But I can't just add something out of nowhere. I changed this. So I've got to unchange it. So really, we want to multiply by 1. We know we need a delta there, x there at the end to tell us to integrate. But we can't just slap it on out of nowhere. There has to be some sort of logic behind it. So we're doing a clever form of 1. Well, we know we want this black delta x to stay outside because we need it to become our dx. But this delta x, we're going to go let it interact with all the other stuff. So we know this is really dividing into each of these. And the reason I can bring it inside the square root is because it is already
Can I do the homework?
a square root.
Whoa. One through one odd, 2, 3, and 4.
Thank you.
So we're going to bring that stuff, that delta x inside, delta x squared inside, to interact with the rest. So we really have delta x squared divided by delta x squared plus delta y squared over delta x squared. And then canceling the square root and the squared outside, we just have delta x outside. What do you see that we can simplify? Delta x squared over delta x squared would be 1. This whole thing becomes 1. Well, if we take the limit of this, because when we take the limit and add all the pieces, the limit is to make that change infinitely small. So if we take the limit and add all those infinitely small pieces together, that's how we get our integral. So we would get the integral. We have 1 here. But since we made this infinitely small, instead of delta y, now we have dy. Instead of delta x, we have dx.
What happened to the square?
It'll be there. I just haven't written it yet.
Oh.
I'm trying to wait to see if you guys make a connection yet. What is that?
DX.
dy dx is derivative.
Oh, yeah.
So it's the derivative squared.
I learned that like 2 years ago.
And then we get our dx outside to say we're adding up all our infinitely small x pieces. So this is our formula for length of a curve. Length is the integral from a to b of the square root of 1 plus the derivative squared. So you could write y prime if you prefer, times dx. So let's write a note card for this as well really quick. We have all our other note card for volumes. So once we have this formula, it's all about plug and chug. I mean, length of a curve isn't really that hard, it's just about knowing the formula. So find the exact length of y equals 4 square root of 2 over 3, x to the 3 halves, minus 1, from 0 to 1.
Is that supposed to be the derivative?
No,
No, so you have to take the derivative.
we have to find the derivative. That is a good point.
I knew that there was something else.
So we need to take the derivative of that function. This one's a fairly basic derivative. What rule do we need to use to find this derivative?
Power
Power rule. So now we're doing power rule, not anti-power rule. So using power rule, we've got to bring the 3/2 down and multiply it by that.
What?
Because we're doing power rule, not anti-power rule. We are deriving,
learned this.
not integrating. I know, it's been a while, and the what will even be more confusing is that we will be integrating eventually.
Oh boy.
So then instead of adding 1, we minus 1.
Oh.
And then what
That's
did I
a
just do?
zero.
This is derivative of
Zero.
constant is 0. So we have to simplify this. So we get 2 square root 2 x to the 1/2. She already left.
Oh, she already left?
Yeah.
All right, thank you.
So we get 2 square root 2. Oh, and what else? Man, my differentiating skills are rusty. dy dx or y prime. I need to say, hey, this is the derivative, so so now we just plug this straight into the equation for length. Length of our curve will be the integral from 0 to 1, because that's what they told us, of the square root of 1 plus that whole thing, 2 square root 2 x to the 1/2 squared dx. Now, for the most part, these must be integrated with your calculator. Because we have a square root with a whole bunch of stuff inside, we need to do u sub, but we're not going to have stuff cancel outside. I guess this one we could integrate by hand. A lot of the times we can't. We'd get 1 plus 2 squared is 4, square root of 2 squared is 2, x to the 1/2 squared is x, so we would get 8x. So just to practice our u sub skills a little, since we're probably also a little rusty on that, what would I set as my inside?
I don't know.
1 plus 8x.
1 plus 8x. What would dx equal? Du divided by
Oh, it would be,
the derivative of that. So this one we could do by hand. We would get that 1/8 out front. We go from 0 to 1 of u to the 1/2 du. And then we'd integrate what's the anti-power rule of u to the 1/2.
it would be, 2,
Close. 2 over 3. Because you have to add the 1 first, then divide. So 2 over 3, so we have 1/8 times 2 over 3, u to the 3/2, but we can plug 1 plus 8x back in. Evaluated from 0 to 1. So now we have to do fundamental theorem of calculus. We can do some simplifying with these coefficients. We get 1/12. Plug in 1. Now this is a case where we do have to plug in 0. Yes, there's a polynomial inside, but not everything will disappear because we'll still have 1 plus 0. So you have to do minus, sorry, that's not 1 over 2, that's 1 over 12. minus 112, 1 plus 8 times 0, the 3 halves. So inside here, what do we really have?
9.
9. Now if we're doing this by hand, again, just to practice, what's my best way to do 9 to the 3 halves by hand?
9 squared, or is it
Then take the square and cube it.
Take the square root first, then cube it. If you try and do 9 cubed, 9 times 9 is 81. 81 times 9 is
a big number?
729. It's a big number. Then we have to try and square root 729. I don't know about you guys, but I have no idea what the square root of 729 is. So,
It's 27.
if we square root first, square root of 9 is 3. 3 to the third is 27. So we'd get 27 over 12.
Oh, you got the same answer. That's impressive.
1 plus 0 is 1, so minus 1/12 is 26 over 12. Or, thank you. So hopefully that is what we got in the calculator. So I'm going to have you guys try a problem.
Oh boy. My world.
This one,
Tell me that there's multiple ways to solve a problem.
this one you definitely will have to plug the integral part into a calculator. This one there will be no way to solve by hand,
Unless you're super talented.
even if you're super talented. Okay, so what did you guys get when you plugged everything in?
2.057.
2.057. Great job for using 3 decimal places.
That's what it is. That's what it is.
Make sure to use 3. Didn't we find a way to actually get it to
You
show
highlight
why?
it and then you press enter again. But it never works for me.
Or you could set it to,
You can set it to fix.
yeah, fix it to 5 decimal places. 'cause
Two
that's the
point
most
zero
reliable.
56999740184.
Yes. Okay, so there's only 2 cases where these kinds of problems could give us trouble.
When Ben is involved.
So, in the instructions are the same, find the length of the curve. So when we take the derivative of this, y is x to the 1/3, I'm going to rewrite it in exponential form instead of radical form. We take the derivative dy dx is 1/3 x to the negative 2/3 and then we know negative exponents move our entire thing attached to the negative exponent to the denominator. So why is this a problem for us?
I'm not checking this.
What about it? The x is in the denominator. So specifically, what point is going to give us trouble?
0.
0. We can't integrate non-continuous function. Well, sorry. We can't integrate
0.
when our tangent line is vertical. We can't integrate at 0 because that doesn't exist. So that gives us some problems. When that happens, we're going to flip the graph to be in terms of y, because then that vertical tangent line becomes a horizontal tangent line. If my graph like this has a vertical tangent line, if we flip it, that's going to give me a horizontal tangent line. So instead of working with our x's, we're going to work with our y's instead. So if I take y equals x to the 1/3, and I want to write it as x equals something, y to the 3rd. We would just have to cube both sides. And that function is much nicer for us. Y to the 3rd. What's our derivative going to be? In this case, dx dy. That's kind of crazy. We're not used to seeing it that direction.
3y
3y squared. Are we going to have any troubles integrating that? No.
Probably not.
So when something like this happens, the only thing we have to remember is that our bounds should also change. Normally our bounds are the first x value to the last x value. But now what should they be since we're in terms of y?
The y values.
The y values. So instead of going from -8 to 8, we should go from -2 to 2. And then we still just plug it into our formula, 1 plus 3y squared dy. So then again, that one is impossible to do by hand. Like I said, a majority of these, even if we tried to use u substitution, it wouldn't work. If we have 1 plus 9y to the 4th, then when we did u sub, dy would be du over 9y to the 4th, 36y to the 3rd. We'd have that extra y that wouldn't cancel out. So if we plug that whole thing into the calculator,
17.261.
now I did experiment on the Inspire. I was like, well, can the Inspire still do it even though this has a discontinuity here, has the vertical asymptote there? When I plugged in using the x values from -8 to 8, it gave me something I had never seen before. I plugged that in, it still gave me 17.261, but it had a little yellow triangle with an exclamation point to the left, and it said, you may not want to trust this answer, basically. I forget the exact words, but it said something about this might not be right. So it could actually still do it in terms of x, the Inspire can, but it'll give you kind of a warning symbol saying, this might not be correct. This is what the calculator's getting, but still might not be completely correct.
Accuracy.
Yes, questionable accuracy, that's their way of saying, probably you shouldn't trust this. Okay, so one last example. Sorry, with the quiz today, we're not going to have time to work on the homework. It's already 2:04. So we'll go through this example pretty quickly. So we have x squared minus 4 times the absolute value of x minus x.
Not the absolute value of x.
Absolute value actually is what causes problems on this current problem.
So I have a question.
Yes.
Why can we deal with horizontal asymptotes but not vertical?
Slope. What is the slope of a horizontal asymptote?
0.
What's the slope of a vertical asymptote? Undefined. So this graph, trying to save time by not actually plugging it into a calculator, but by looking it up in the book, looks like this. So what's the problem with that graph? Cusps. Cusps are issues. Cusps are not our friends. So when there's a cusp, we have to split up our integral into 2 pieces. And we have to know what we mean by absolute value. We know absolute value functions are actually piecewise functions. We're going to run out of time.
Oh, that's so short. I know. It's okay, we can skip the homework page. Oh, see that.
Okay?
This is America. We go by diplomat, not dictatorship.
As soon as you can say it right, maybe you will.
That's way better than normal. So we've got to split this up. when we have absolute value, it means two possibilities. Our first possibility is when this value is positive, it doesn't do anything. If our numbers in here are positive, they stay positive. So our first possibility is nothing changed when our x values are positive. Our second possibility is, if I plug in a negative number in here, what do I have to do?
Maybe positive.
Make it positive. Well, if I have -2 and I don't have the absolute value bars to make it positive, how do I make it positive?
You minus it.
We have a negative -2. So we've got to do that except with the x. X squared minus 4 negative x, which is always kind of weird because we think absolute value, everything's positive. So it's weird for us to come out with a negative because of the absolute value.
Can't you just put like plus 4x?
Yeah, you could, but I wanted to show that. So now we just have to decide, we can simplify these, but we're running out of time, so I'm not gonna write the simplified form until we write the integral. We're gonna integrate from -4. Where should I stop my first integral?
0.
0. So that's where my cusp is. So all of those numbers between -4 and 0, they're negative values. So which function should I use?
-1.
The bottom one, because it's all the values less than 0. So if we change that to positive 4x and combine, we get plus 3x. And then we have to add the other integral from 0 to 4. This time we use the top function. And then if we were to plug that whole thing into a oh wait, sorry, what did I do wrong? Pay attention, Miss Barton.
You didn't do the square root and the plus.
I didn't do the square root, I didn't do the derivatives. Man,
You just type
I was in such a rush. Blech.
such a rush you can't even say rush.
I know.
Josh is making fun of people today. Don't worry about it.
So, I should have done the integral of 1 plus, and then the derivative of this, so this was x squared plus 3x, so our derivative would be 2x plus 3 squared.
I'm running out of room. I don't think I have room for homework. Dang it.
Dude.
Integral from 0 to
Go
4
to
square
fabulous.
root,
I fixed it.
1
Oh,
plus
don't do that.
2x minus 5 squared. I apologize, I'm sorry, I was just trying to rush through this so we could have the homework assignment up.
Oh, that's okay. We understand.
We're gonna have the homework assignment out.
Yeah.
You might have to copy it for like 5 seconds after the bell.
Oh, can't do it now.
Oh, I didn't
You
copy
can.
the rest of the assignment. I mean,
You'll survive. It's on YouTube.
Stupid. No.
Glad we stored the lectures.
of course, if she hadn't like gone to this page, then it would have been on the recording. So.
But I did, and it is. So do your homework.
Stupid as Barton.